Hi everyone, I'm Brady Volpe, founder of Nimble This and the Volpe firm. This is Get Your Tech On, our show on all things DOCSIS. We're back live this week. Our show today is troubleshooting in-home impairments with P&M, full band capture, and RxMER. With us today again is John Downey, Senior Technical Leader at Cisco Systems. John, welcome back. And where are you broadcasting from today?
I am in the chilly section of Northeast in Pennsylvania. I just took a little vacation and come up to see some family up in PA.
Well, I really appreciate you joining us back, even though you're, not back in your home state. But say hi to everyone in Pennsylvania, where I'm also from. So, as we said, we're going to talk a little bit about P&M, some troubleshooting, understand, how to troubleshoot in-home impairments. I have some slides I'll be presenting. Some of this stuff is material people have seen before, but we want to do kind of a deep dive into some of the nuances of really understanding how to troubleshoot in-home impairments. I'm going to start off with a first slide here, which I think is really core to understanding something about P&M that a lot of people kind of trip over sometimes when they start using it, and that's really understanding we don't start troubleshooting problems from the back of the cable modem. So I want to throw up this first slide. John, we started talking about this a little bit. So often subscribers create problems on their own when they start adding splitters, maybe on the back of the modem. And a lot of times subscribers don't understand necessarily how splitters work. And so in this first example, I have a very common problem that we run into a lot, and that's subscribers putting in splitters the wrong way. So I'm showing a backwards splitter here where, maybe someone has a modem in their house. They want to add some, another TV or some other device to that. They install the splitter wrong, and that creates a micro reflection within the home. So what we're showing here, some in P&M applications, we show digital taps. Those digital taps show some type of a distance to where that impairment is. And what we're seeing here are, this splitter, an echo cavity, the pre-equalizer of the cable modem showing a 250-foot echo cavity. So often, people assume that echo cavity starts at the back of the cable modem, and that's not actually what's happening. That echo cavity starts at the back of where that reverse splitter is. That could be anywhere inside the home.
So this is interesting because, the insertion loss on a splitter is the same, front, back, back, front. It's that port-to-port isolation. So in your diagram here, the TV would get screwed, right? The TV would be getting like 20 dB lower than it should be. What I could see happening here is the modem transmits in the upstream, hits the back of the TV that has a poor return loss to begin with, and reflects back and forth right there. So having that leg go into the modem, that through loss of that leg is the same regardless of it turning around or not. But the fact that the modem's transmit signal can easily get to the TV, that's where you're supposed to have isolation. Well, you don't. You have that cable modem transmitting right to the TV, reflecting, going back and forth, probably right back to the modem. I would say that reflection really is, in this case, it is probably from the modem to the TV, back and forth, back and forth, back and forth.
It's actually correct what you're saying, because the modem itself can become its own, the modem will reflect the signal back because you have these reflections going around.
And its return loss is probably no better than 6 dB or so.
That's correct. Like most devices have a really bad return loss, or they kind of create their own impedance mismatch in the network. So you have the splitter that's creating an impedance mismatch. And when we talk about impedance mismatches, we're basically, the entire cable plan is supposed to be 75 ohms. When you introduce a device that's creating a non-75 ohm reflection, we no longer have a non-75 ohm cable plant. And all the RF signals are really happy. I usually use a highway as an example, where if you're going down a 75 miles an hour down the highway, all cars are happy until you hit a construction or an accident or something like that. Now it's no longer a 75 mile per hour highway. And that's when traffic backup's happening. The same thing happens to RF signals. When it's no longer a 75 ohm impedance coax plant, dense in cables, reverse splitters, a 6 dB return loss modem or TV set.
Go back to that diagram, and let's do a hypothetical. Let's put the modem and the TV and swap them. what I can see happening there is the modem would have to overcome more loss for port-to-port isolation to get back to the CMTS, so it would transmit hotter. And because it transmitted hotter, it would find its way to the TV on the other connection, right? Because we're going to swap them.
Right.
And you'd probably have even worse reflections. Same cavity, but it would be much worse in power level.
Correct. And so just just to explain, verbalize what's happening with those digital taps on the right side, every cable modem has, well, DOCSIS 2.0, 3.0, and 3.1 cable modems. They have a 24 tap digital pre-equalizer in them if they're using SC QAM channels in the upstream for 3.1 cable modems. And that's pretty much what we're seeing there. So that digital pre-equalizer, when the CMTS sees that the cable modem is having these reflection issues due to micro reflections, the CMTS talks to the cable modem and it adjusts the pre-equalizer, those red bars that we saw. It adjusts that pre-equalizer so it allows the cable modem to compensate for those micro reflections in the return path.
Yeah, the analogy I make is there's 24 like sampling points. It's like in a time domain, but there's the bigger the channel is, single carrier QAM channel, 6.4 megahertz is the biggest you can make. You have 20 sampling points. And when you do that, you could get a very tight standing wave within that 6.4 megahertz, which then can be translated to what's the biggest cavity or longest distance I could correctly or accurately troubleshoot. So if it's really tight and I have 24 sampling points, I'm going to have 12 peak to valleys, right? Up, down, up, down, up, down. It'll be 12. So you could figure that out. And Ron's always done the math, and it basically came out to like the biggest or longest distance you could find would be like 200 and some feet away or something like that.
Yeah, there's there's a whole Cable Lab specification on the PNM best practice for the best practices for it includes that formula if anyone's interested in looking that up. So I want to move on to the next one here, John, because we get into we start to expand now on the pre-equalizer taps and how we can interpret that. So on the right hand side, the bottom right hand side, once again we see the 24 cable modem pre-equalizer taps. There's two different colors there. That's because there's two upstreams. So we see 24 pre-equalizer taps for the two different upstreams on this modem. And we can see again, there's high elevations of these pre-equalizer taps. That's an indication that cable modem's working really hard to compensate for some problem. On the left-hand side, there's something we call ICFR, in-channel frequency response. I think you had you call it peak to valley early. We also call it peak to valley. You can kind of imagine these two lines on the left-hand side as being the very top of the cable modem haystack. So if we were to zoom in on cable modem haystacks in the upstream, if we looked at a spectrum analyzer and we looked at cable modems transmitting in the upstream using SC QAM, we zoomed in on the very top of those. Ideally, they should be nice and flat when they go into the CMTS. When they're not nice and flat, that tells us there's some type of impairment that the cable modem's pre-equalizing its output. It's kind of doing something really funky here, and we call that it's a peak to valley variation of the top of that cable modem haystack, which we generally call ICFR, in-channel frequency response. And when we're talking about in-home impairments in PNM, proactive network maintenance, generally when all of the upstream channels that the cable modem's transmitting from have a peak to valley or an ICFR of greater than 3 dB, which this cable modem does, almost all the time, that's an indication of an in-home problem. What the in-home problem is almost generally some type of bad in-home wiring, bad drops, or something related, very, very close to the subscriber's home. Could even be at the tap. In this particular case, I'm going to go and show you what the in-home problem was we found. Here we see the source. It's bad. I think we normally call these twist-on connectors. So you can just finger tight these connectors. No compression fitting. So anyone listen to the audio here, we're looking at a two-way splitter where on the input side of the two-way splitter is a really old weathered-looking twist-on F connector, and on the output are two weather-worn twist-on F connectors. So that, basically we cut these connectors off, also replaced a splitter with new compression fit connectors, And after doing that, moving on to the next slide, we see that what was previously a much greater than 3 dB peak to valley is now within plus or minus 1 dB peak to valley, except for one channel. It still has a little bit of group delay. And group delay is kind of explained by the digital taps on the left-hand side having a little bit of a ramp up. So oftentimes we get a little bit of group delay in the plant. I think we've talked about group delay before, but I'll let you take that one, John.
So on the right side graph, you're showing the taps. And to explain to the audience, because we kind of don't have a mouse to point to it, the biggest tap is your main tap, right?
Correct.
Anything to the right of the main tap usually is indicative of microreflections and things of that nature, impedance mismatches causing microreflections. Anything to the left of that main tap, it usually indicates group delay problems. And we know group delay problems, a channel going through a filter, it has a little bit more delay at the top end of the channel versus the bottom end of the channel. Like if I do a 42 megahertz filter and it's a pretty decent roll off of 42 megahertz, if not 40 megahertz, if I try to put an upstream channel at say 38 megahertz, the edge of a 6.4 is going to be right at 41. Yeah, there's some built-in filter alpha in the channel itself, but you're still going to get some delay and some roll off. So sometimes you won't see the roll off, so the in-channel frequency response will look nice and flat, but there's still time delay because of your LRC, which is inductor, resistors, and capacitance. That circuitry is going to cause delay. Eli the Iceman. Right.
Eli the Iceman. I've not heard that for a while.
Eli the Iceman. In a inductive circuit, voltage leads current. In a capacitive circuit, current leads voltage.
Correct.
Eli Iceman.
Eli the Iceman. Like Electronics 101.
Yes, exactly.
So when we're talking about group delay, we normally see that close to the diplex filter. The diplex filter being a low pass and high pass filter in RF amplifiers, fiber nodes to separate the return from the forward. We know there's a DOCSIS specification. It says our group delay should be less than 200 nanoseconds per megahertz, which that's awesome. But when we look at P&M, when we're using pre-equalizer and cable modems, we often see group delay being much, much higher than 200 nanoseconds per megahertz. In fact, in here, I think it's like 14 or 1400 nanoseconds per megahertz. So I often have customers saying, when we're using pre-equalization, what is an acceptable group delay in the upstream? Because we're far exceeding the DOCSIS specification of 200 nanoseconds per megahertz. Now, I was curious if you had any thoughts on that.
And pre-EQ is masking it, right?
Correct.
We're using pre-EQ to mask it, and it's cumulative. So you could have a step attenuator, you could have a house amp, you could have 7 amplifiers in cascade, then the node. All those filters are adding and adding and adding and adding and adding. So yeah, the group delay, easy way is stay away from the filter, roll off. But I mean, we're trying to squeeze out as much as we can from our upstream spectrum. So we're trying to squeeze out what we can. Some people would argue, why not do a more narrow carrier near the band edge? Because then you have less group delay because it's a smaller channel.
But that's the cleanest. That's the cleanest part of our spectrum. So we like to have the 6.4 megahertz there because it has more bandwidth.
Yeah, I'd like to do OFDMA there.
So
that's
when you're stuck with a 42 megahertz return, I mean, a lot of operators are pushing their DOCSIS channels up as high as they can. They want to have at least 4 DOCSIS channels in a 42 megahertz return. We need more spectrum in that 42 megahertz return. What I've seen is, up to 2000 nanoseconds per megahertz really doesn't impact subscribers as long as we have pre-equalization turned on. And that's kind of what I'll tell customers is, you can run that high as long as you have pre-equalization turned on. It has pretty minimal impact to end users.
Agreed. But with that said, I bring this up because, and I think this too, we've had some problems with OFDMA and pre-EQ, like out of the gate. There was times where the upstream levels for OFDMA were fluctuating, which then fluctuated the MER readings. And it turned out it was the pre-equalization, like the algorithm was not baked in very full on early modems. So I tell people, it's like, if you ever see OFDMA upstream fluctuating levels or MER, turn pre-EQ on and off and see if it helps. It would just be another data point to prove if that's the problem.
Yeah, and
And
I've,
there
I've
should be
seen the same
firmware
thing.
fixes for that.
Seeing the same thing as well with pre-EQ on DOCSIS 3.1. Not DOCSIS 2.0, DOCSIS 3.0. Pre-EQ is solid as a rock for those modems, so I'd never encourage anyone to turn it off for that. But with DOCSIS 3.1, it does seem like we're continuing to grow with maturity on the pre-equalizer in DOCSIS 3.1 modems for OFDM-A and also OFDM. But I do think that's something that's continuing to get more and more robust, and would encourage people, as you're saying, turn it on, see if things get better, or turn it off if they don't.
When you think about a single carrier QAM with a 24 tap, now with OFDMA, you have all these subcarriers, so you really don't have a 24 tap per se. It's almost like every subcarrier is a tap, because every subcarrier can adjust its level. So we have this initial ranging, we have the spine ranging, and then we have pre-equalization as well. So everything could be slightly up and down on a per subcarrier basis.
Correct.
Yeah. So if I have an in-channel frequency response, I can offset it, like pre-distort it on a 50 kilohertz or 25 kilohertz granularity because of all the subcarriers.
Correct. So before I move on to the next one, I'd just like to take a moment and ask everyone watching, please do smash that thumbs up button and subscribe. If you've not already subscribed our channel, hit the notification bell so you know when our next episode is coming up. I greatly appreciate that. Our next one, so we talked about 42 megahertz. We got some comments in, so thanks everyone. If you do have questions, please feel free to drop them in to the chat window. We'll be glad to take any questions you have on this topic, or pretty much any other topic you want to try to stump us with. On our next topic here, so we talked about 42 megahertz return. A lot of operators are moving to 85 megahertz return. Some are even considering moving to 204 megahertz return. One of the interesting challenges that everyone has to keep in mind is some subscribers have their own in-home amplifiers. And even though you're upgrading your plants, you may not be upgrading your subscribers' in-home amplifiers. And that can have some unique consequences on the cable modems behind those amplifiers. And this is one of those examples that we can see really well with P&M. So at the top here, what I'm showing is the cable modem itself is able to, it's aware of the bonding group that it should be locking to. So, basically the cable modem says, hey, I know I have 8 upstream channels that I can be transmitting and communicating with the CMTS. However, what we're showing is the 2 of those channels are locked, green, and happy. One of those channels at 43.5 megahertz is red and suffering some severe performance issues. And we can see that on the bottom. On the right-hand side, we see the pre-equalizer tap chart. Most of the digital tap charts are pretty happy, except we see one has a lot of, as we talked about before, group delay. We see that group delay because, as John mentioned, all the taps to the left of the main tap number 8, or digital tap number 8, they're really severely elevated. Now, if we look at the ICFR, the in-channel frequency response, we can see that there's severe ICFR, or peak to valley, on the highest frequency channel. And so so there's a few things going on here. First of all, the modem is in what we call partial mode, because that modem cannot lock or cannot bond to all of its 8 channels. And that's, again, it's because there's an in-home amplifier. And that, theoretically, that may not be such a bad thing. Where I see the really challenge here, the big challenge here, is that 3rd channel, the highest frequency channel, is kind of really severely impacted. So when that subscriber is transmitting data in the upstream, 2 of the channels are really healthy. But that 3rd channel, the highest frequency channel that's close to the diplex filter in the in-house amplifier, if it's impaired enough, we call that an impaired channel. So it could get uncorrectable code word errors. The group delay on it could be well more severe than that 2,000 nanoseconds per megahertz that I talked about. And when we transmit data on the upstream, we don't necessarily know exactly what data is going to be transmitted on what upstream. And John, I think we've talked about, we generally spread data across all 3 upstreams in this case. So some of that data could take some pretty severe errors.
So, I mean, I think the ultimate goal is we're trying to figure out how do we find and target houses that are legitimate or are going to have problems before we even get there. So I could see where, say, you're doing 4-channel upstream bonding and you're like, I'm going to upgrade to 85. Let's just throw a channel near the roll off of, say, 45 megahertz and throw it into a bonding group. And then we can maybe use P&M to identify all the houses that are going to cause us problems before we even activate the 85 megahertz. Because even though a modem might say it supports 85 megahertz, it might be the chipset supports 85 megahertz. Doesn't mean the built-in diplex filter was 85 megahertz. It might have been a hard set 42, and you were supposed to order 85 or software configurable diplex filters. And then let me throw another one at you. Is I've seen a case where I had a modem that would support 85, and when we turned it on, it switched on the 42 and the 85 filter. So it supported 5 to 85, but right near where the two built-in filters overlapped, the channel right there had group delay problems and some in-channel frequency response problems. So the fix there was we just stay away from that range. Like I could easily put 4 more upstream channels at 50 to 85. You know, I only need 27 megahertz to get 4 more channels in.
Yeah, so I think
I always recommend not putting a channel near the 42. In this case, I would do it at the beginning just to identify the bad houses and the bad modems. And then when I really deploy, I'd never put a channel right there at 45. I'd put them all above, say, 50 to 85. That way I'm staying away from that troublesome area.
so I think you bring up some really good points, John. If operators aren't careful, they could get modems or configure modems that don't go up to 85 megahertz, not configured properly. Then after that, just the way you configure your channels could prevent this partial or this impaired service mode channel. Not putting a channel right where we know there could be a diplex filter in a subscriber's home could prevent this impaired service that we have right away. And that's a pretty important thing to throw out there for people to think about.
And to pile on, I don't want to be the bringer of bad news, but to pile on, because a lot of times partial mode might be dictated by upstream station maintenance, and station maintenance is a 16 QAM, you can have a case where the MER is like 20 dB. You're dropping every single packet on that upstream because it never went to partial mode because the station maintenance is still working.
Yep.
So there's cases where you don't go into partial mode quick enough and you wanted it to, and you're dropping all your frames on that one upstream. Yeah, so you have to understand, like, how do I track it? How does partial mode go in and out of partial mode? Or do I just, sometimes an ounce of prevention is worth a pound of cure.
Yeah.
If maybe I don't even use that frequency, I don't have to worry about going into partial mode.
And depending on the signal level meter that you have, this could be something that's a little tricky to identify when you go to a subscriber's home and lock on with your signal level meter. I mean, if you're just looking at downstream levels, you're never going to see this. You have to lock on with your signal level meter that can do a full DOCSIS test. And that signal level meter needs to look at every single upstream that the cable modem is doing, and you basically have to perform the DOCSIS test where the cable modem is. You can't just go to the subscriber's drop and do a DOCSIS test there, because if this is indeed not the issue that John was talking about, where we have a misconfigured modem with a diplex filter in a modem, if this indeed is a house amplifier, you have to perform that test right where the modem is, so you're seeing the same house amplifier that the cable modem is seeing.
Here's the conundrum. You already have a customer. You're not going to send a truck or a technician to a house that's already set up.
Yep.
You just want to upgrade them to 85. So how do I do that remotely, right? So we're talking about using P&M to remotely test it. And then if it's not going to work, then the technician's probably going to go out there and either replace the modem or at least use their test equipment to prove that modem, that house setup is good. But ultimately, we're trying to do everything remote as much as we can, right?
Due to COVID, we're trying.
Yeah.
I mean, that's a big driver behind this. Is so many times people won't let us go into their houses, particularly if we have another spike coming up.
Yeah.
So that's a big thing there. We have a question from LC that says, so what issues would you see if group delay is too high? And I'm going to say, I use the words of Ron Rannick, it depends. So, we have different services that we use in the upstream. The upstream is where we'd get impacted by group delay. If we're just checking our email, maybe if we're just using some type of service that is a TCP based service, TCP being that, a type of service that we can retransmit a packet if that packet gets lost, we probably wouldn't notice any difference. If we're using a UDP type service, so that means we don't have the ability to retransmit packets. This is kind of assuming that the group delay is bad enough that it's going to cause uncorrectable code word errors. That could cause issues with like voice packets being dropped. It could cause issues with really bad gaming performance. I've seen where group delay gets high enough that it will cause the modem to deregister and come back online. John, what have you seen from bad group delay?
So, I mean, this is a couple of different ways of looking at it. Is group delay is going to cause poor MER. MER has a threshold. So if the MER is decent enough, you might have no problems because you're doing 64 QAM in the upstream. It'll break about a 23 dB MER. Group delay might have dropped you from a 30 to a 28 and you're still running fine. Or you look at it another way is the group delay was bad. Pre-EQ is masking it, but you are now eating away at your pre-equalization robustness or the amount of pre-EQ you can do, right? Because you're trying to make up for some of the group delay with the pre-EQ. So now you have one little spike or the weather changes, and now your pre-EQ has to work even harder, and it hits the fan.
Yeah, I think I think that's a good point that I didn't mention, but I normally try to mention to customers when we talk about group delay. A cable modem's pre-equalizer has only so much capability to compensate for impairments. And we talked about the main tap. So that's tap number 8 in the pre-equalizer. So when the cable modem pre-equalizer starts running out of the capability to compensate for impairments, that main tap starts to get compressed, which means we pull energy from the main tap to put it into the other digital taps in the cable modem's pre-equalizer. When the main tap gets compressed, it's called main tap compression, or MTC. And that is one of the very common metrics that we have in any P&M application that we look at is, how bad is the main tap compression, or MTC, of any modem? When the MTC of any cable modems hits 0.5, we consider that modem starting to get into a critical condition because the pre-equalizer in the cable modem is, like as you said, it's starting to run out of energy. It's starting to run out of steam. It's not going to be able to compensate for future impairments. So if we allow a cable modem, that upstream for the cable modem to be in kind of a saturated group delay state, now when some future impairment comes along, you've pretty much used up your pre-equalizer. And that channel that's in a group delay zone will just go offline. And now, or it'll become so impaired that it'll have very high uncorrectable code word errors. So it's kind of a trade-off, and that is the trade-off you do when you allow an upstream channel to be, really deeply saturated in group delay.
Yeah, and like we talk about, most people equate group delay with roll-off of filters and stuff like that, but you could have a micro reflection cause a standing wave, and the standing wave looks like a filter.
Yep.
So the standing wave is creating an in-channel frequency response, which then also causes group delay. So I used to say, well, group delay should be fine if you stay away from diplex filter, but you can still have group delay on a channel that's right in the middle of your spectrum.
Correct. So speaking of standing waves and filters, I want to go back to the slide here and talk about. So last episode we talked a lot about full band capture. So if anyone's not familiar with full band capture, please go back and watch our last episode. Here we see a full band capture that has a little bit of a standing wave in it, and more severely, we see a lot of high frequency roll-off. So if those are DOCSIS channels, the modem may have a problem locking to those highest frequency DOCSIS channels. If they're video channels, set-top box may have difficulty locking to them. We got macro blocking. Basically, we get subscriber calling in and complaining about their service. We looked at the root cause of this. We found that this was a bad drop. So, again, we're talking about bad drops, subscriber issues, specific individual subscribe issues. So some of the channels between 4 and 500 megahertz had dropped in level to as much as negative 10 dBmV. We replaced the whole drop, and what we found is, as we're showing in the picture here, there was a J hook into the telephone pole where we had, that was basically what was connecting the drop or holding the drop up in the air, going down to the subscriber's home, and that the coax cable itself was wrapped so tightly around the drop, it had created a kink in the coax cable. So we've talked before about, we don't like to use staples in coax cables or anything that's going to create too much of a bend in the coax cable. That creates a kink. Now, down on the side of the house, there was also some corrosion on the connector. And now we have 2 points where between the kink and the corrosion on the connector on the side of the house, we create what we call an echo cavity. We've talked a lot about echo cavities where the signals will bounce back and forth from both a cable modem and also in the downstream, and that creates our standing wave that we see in the full band capture. So this is these are our micro reflections that we talk so frequently about, and it just creates a little bit of dent in that. Creates a non-75 ohm impedance mismatch in our coax cable.
So the ingress is so bad you named it twice. The first bullet point says FM ingress. I'm like, okay.
Yeah. Also, so that was some of the other thing that's going on. If you look at the low frequencies, and I didn't zoom in on that, there was a lot of FM ingress coming in. So I think there was enough abrasion in this, or I don't remember exactly if it was from a loose connector down at the house, but this also allowed FM ingress to come in at the very low frequencies. And we know that when there's FM ingress coming in, oftentimes that means there's return path noise that comes into return. This particular house was allowing a huge amount of return path ingress. And that was really the reason that we visited this house, was a massive amount of return path ingress that was coming back all the way to the CMTS, which then, as we know about the funneling effect, impacts all of the subscribers. But when we got there, we saw it had other issues as well.
And that's the concern when you go 204, right? Talk about FM downstream. Well, FM now is going to be upstream. Our return path ingress could be FM radio.
Yeah, and oftentimes we see FM, we use FM ingress many times to identify subscribers' homes that are also leaking return path noise back up to the head end. It's a very common indicator. So our next one, another filter example. So probably most people who work in the cable industry have used or come across, subscribers who are data-only subscribers. They don't want the video channels. They just want DOCSIS only. And a common way we've done this historically is to put on these little tiny traps. Arcom's a very prominent vendor of these traps. They make super tiny traps, and the purpose of these traps is to block all of the video channels that are data-only customers. We don't want them to get the video channels. More and more often, we're not using these because the set-top boxes are more intelligent. We encrypt all of the video channels, but there's so many of these video traps out there. We've deployed them, we forget about them, but we still have customers that maybe they want the video channels now, or maybe someone moves out of a house or apartment and someone moves back in, and now they want to do an upgrade and get the video channels, but we have to go find those traps. And using full band capture is a great way to be able to identify first if that trap exists. It also can identify if a trap is bad. Sometimes these traps get zapped by lightning or voltage, and it can really cause the trap to not perform the way it was designed. So that's a fantastic use for full band capture to identify these traps.
There was even some MSOs that wanted to put OFDM from 258 to 350 or whatever, 192 megahertz. So 258 to 450, whatever, 450. So, but then these traps would block the OFDM signal. So they still want to do high speed data, but they want to do higher speed data. They want to do DOCSIS 3.1, but the MSO wanted to place the OFDM on the low side to get better response and higher MER, higher modulation. But then these traps would impede that.
Correct. So it's like a matter of just going out and finding them, and they are everywhere in plants when you start looking around at full band capture signals.
But like you said, you should be able to do full bandwidth capture and identify the locations before you even go out there. Like if I know if someone's going to upgrade to 3.1, I'm going to do the FBC from the 3.0 modem before I even go out there.
Correct.
You know,
Absolutely correct. So the next couple of slides I have show that sometimes subscriber in-home issues can impact more than just one subscriber. And what I'm showing on the map here are two subscribers side by side. They both have an eye on them, and the eye means that they're intermittent. We see that a lot of times. Sometimes, we have subscribers that are intermittent, meaning that their transmit signals fluctuates over time. And cable modems should have a pretty consistent transmit power from one day to the next. It shouldn't vary over time. We'll see that both of these modems have a varying transmit power from just throughout the day. That's not a good thing. We'll talk about why.
I mean, temperature wise, we can see a swing, but it would be more like in the heat of the day, it's hotter out, so it transmitted 50, and then it got cool at night, and it was all the way down to 48. But it shouldn't be going up and down throughout the day.
Correct.
You might see a pattern there that makes sense with the daily routine, right, or temperature fluctuation. That's it.
Correct. And the other thing that we see with both of these modems on here, going back to the slide, is we see that there's a suckout just above, I think it's 200 megahertz there. So we see the same suckout in the top slide to the bottom slide.
I gotta put on my glasses.
Yeah, so we see the same suckout on both of these subscribers' homes. So we have a suckout, and then if I go down to the next slide, we can see that intermittent issue that's going on. So that red line on the top shows transmit power. So you said, from day to night, we could see maybe transmit power of 48 going up to 50, like a 2 dB variation. What we're seeing in here in the variation is a transmit power going from 45 dB up to about 57 dBmV. So that's pretty excessive. That's a pretty significant and that's not from like day to night. That's like during different polling cycles that we're getting on both of these modems. So we're seeing like a 10 dB transmit power in the upstream. And one thing we know is that when you have a lot of variation in transmit power on cable modems, that's normally indicative of a compromised shielding. So that means you like have loose connector or cracks in your connector or something like that. What we found on this particular issue is we had a loose connector right on the tap going to both of these cable modems, and that was not only causing that suckout that we saw. So once we tightened the connector, the suckout went away, but also this intermittent transmit power on the cable modem went away as well. And the leak that we saw, the return path ingress that was coming from these cable modems, also went away. So this was like
what's the green lines?
So also,
what are the green lines?
Yeah, so there's some more things that we do with this in our intermittent modem report. There's a yellow line on the bottom, and this was actually based off of a Cable Labs. So Cable Labs designed this intermittent modem concept here, where the red line tells us how much the modem is transmitting. Its transmit power is varying over time. Okay. The yellow line is sort of a measurement of how much the non-main tap digital pre-equalizers are varying over time. If the modem sees a lot of noise, so, sort of a lot of noise from the house or a lot of noise from the plant leaking into it, it'll cause the digital pre-equalizers to jump around a lot. The green lines are indicating that when the cable modem's transmit power varies a lot, and we're also at the same time seeing the yellow line vary at the same time, we're getting a correlation between transmit variation and noise kind of at the back of the cable modem. It's that kind of a rough analogy of what's going on there. So that green line just telling us we have a correlation between transmit variation and noise at the back of the modem. And that gives us a very high confidence factor that these particular modems or these particular subscribers are letting return path noise back into the plant, which then impacts all other subscribers.
Good.
So that's our intermittent modem that we looked at. So kind of like following the theme of loose connectors, we see a lot of times where low signals into subscribers' house, and this is using full band capture again. So what we see here is all of the RF signals going into this subscriber's home are very low. So at that very high frequency, the highest frequency, we have an RF power of minus 24.9 dBmV on this particular capture. And every time we would recapture the full band capture on this modem, that power level would vary pretty dramatically. Like sometimes it'd be all the way to minus 24.9, sometimes it'd be like minus 10 dBmV. So there'd be huge swings. And if you look at the full band capture, what you see is that it almost looks like there's a standing wave, because there's very large variations in channel power between the full band capture signals between every channel. And that's because as the modem is building, the analog to digital converter is capturing the data, it actually captures it in like 7 megahertz chunks. So when it's actually capturing those 7 megahertz chunks of data, that loose connector on the back of the cable modem is actually capturing different power levels, because the connector is so loose. Every little capture captures a different power level and looks like a standing wave, but it's not actually a standing wave. When you tighten up the connector on the back of the cable modem, that signal power goes right up to where it should be, between, plus and minus 10 dBmV. And so again, we try to spend a lot of time, both educating technicians and as well as subscribers, the importance of just tightening connectors in the back of the cable modem, at the plate, at the wall plate on the wall, and as well as anywhere else that they may have connectors in their house, because a loose connector can be what's causing a subscriber's performance issues.
But on the flip side, people get a little overzealous and they crank them down, they break them.
Yeah,
So
it
it's
doesn't have to be gorilla tight. It just has to be, really a good finger tight.
Yeah.
So very, very common issue.
And I want to point out another thing is, like, it's awesome that we have this visibility, full band capture, but we don't have it unless the modem's online.
That's correct.
It's not like we have access to a device that's a spectrum analyzer unless it's locked on. We're still doing SNMP. We're still trying to get, which is layer 3 of the OSI model, right? So we need connectivity. So we need to be able to get to that device to then pull the information out. So, but it's awesome that we have that visibility, and we can look all the way down to like the noise floor. It is like a spectrum analyzer, right? I mean, you said minus 29. I mean, if I was trying to lock on a channel at minus 29, it wouldn't lock on. But since my primary downstream was probably at the lower frequency, it was probably locked on at like 0 or minus 2 or minus 5. But then I could still get the full bandwidth capture of everything.
Yeah, you just need one downstream DOCSIS channel and one upstream DOCSIS channel in order to get the full band capture capability. But to your point, if you have no DOCSIS connectivity, then we don't have full band capture. You're going to have to send a tech out with a meter to do that same measurement that we're doing right now. So that is a limitation of it.
You might be able to call the customer, and they can go to the old 192.168.100.1 built-in log page of the modem while it's trying to go through its process, and maybe you can get the logs from them or something, right? Maybe they can say, oh yeah, my levels here say it's like minus 20.
And it's almost so, we get a lot of input from subscribers that actually are becoming more and more tech savvy with their own logging into modems, seeing signal levels. But I also see cable operators that are locking subscribers out of that page. And to your point, that might be a reason for cable operators to still allow subscribers to get in. And I could see, more in the future where there is better communication between cable operators and subscribers to have that feedback, where if they can't get, if they're not getting the data, they could have just some sort of portal where subscribers can upload a diagnostic page, or they can push a button and have all the modem data dumped and then sent back to the cable operator.
A lot of people would like to do their own due diligence. I don't like to try to call tech support and then have to wait and then wait and wait. I'd rather do a little bit of due diligence myself say, hey, I checked this stuff out first before I called, and I'm stumped.
Yeah, and I think there's a lot of subscribers out there like yourself, John, who want to do and fix their own issues because they're technical. More and more people are becoming more and more technical in today's world. So last week we talked a lot about last episode we talked a lot about using RxMER per subcarrier to troubleshoot OFDM channels, and I mentioned a lot of times you can't see impairments using full band capture in OFDM channels. In this next slide, I found an example where it actually, you can, I found a modem that was so severely impaired in the downstream that using full band capture almost directly showed what you would see in the RxMER data, but it has to be really severely impaired. So I'll put this slide up, and on the right hand side we're showing full band capture, and this is just an individual subscriber's home that is impaired. The rest of the fiber node was in great shape, but we have severe roll-off going into this subscriber's home. I don't have the answer why this subscriber had such bad roll-off, but there is something, and it is perfect tilt going down in.
But yeah, exactly. The graph on the left is showing all your single carrier QAMs, your OFDM, but it looks like linear tilt or even non-linear tilt, but doesn't look like roll-off.
Correct. And I looked at the subscriber's home around, and they did not have this tilt. So I almost think this subscriber must have an in-home amplifier or something like that. It just had nice linear, it's beautiful linear tilt, actually. It's really horrible performance for them from a data standpoint. But when we look at the OFDM channel, which is 700 megahertz up to about 900 megahertz, we can see that is very, very low in RF level. And then on the right-hand side, when we look at the RxMER per subcarrier, we see the same linear tilt in the RxMER per subcarrier. But the problem is here, I have a red line going across the 29 dB RxMER, which is the threshold for 1024 QAM. And we can see that the RxMER is just at and going below that red threshold line, which means this subscriber's modem will just be on the threshold and below the threshold for 1024 QAM, which would be, I'm not sure. And I actually asked you if you would know, John, what would, in your mind, what do you think? Would this modem support 1024 QAM, or would it be forced to drop down to 512 QAM?
Well, is that the threshold from Cable Labs?
No, this is actually the field threshold for what we would support. So we're right on the real world threshold for 1024 QAM.
Yeah. So they probably have their CMTS set up to have a little bit of buffer, and then you look at that amount of below that threshold, it's probably more than 20% of the total channel, right? I'm just eyeballing it.
Yes.
And I see the clean areas, you probably have exclusion bands.
Correct.
For LTE.
And other known ingressors that are in the plant.
Broadcaster or something, right? So that spectrum is probably more than, me and Jason Miller said, exclude about 10%. And because of how robust it really is. But the amount of spectrum you have there below that red threshold is probably more than 10%. It probably looks like 20% of the channel.
Oh, it's at least 20%, yes.
Yeah, it's going to drop down to one order lower, or maybe two orders lower. So it might drop down to say 256 QAM, which is not what I want, right?
No.
Never want to drop 256 QAM. Hell, I can do that with single carrier QAM. Why would I want an OFDM to be doing 256 QAM? I'd rather that modem maybe go to partial mode in that case.
So it dropped back to its SC QAM carriers then.
Yeah, quit wasting my time with low modulation for this one modem, because remember, you're sharing an OFDM with everybody else that might be running higher modulation. So why would I want this one modem running low modulation? You can argue that sometimes there's an inflection point where I'd rather that modem go to partial mode.
Right. And so the rule of thumb you use is about 20% of the subcarriers. If they're below the threshold, then the modem will typically drop to the next lower modulation that's available from the CMTS.
Me and Jason, we settled on 10%.
Okay.
Just ignore 10%, because you can have some roll off, And to change modulation because of 10% of your spectrum is not in our best interest. We're
Right.
trying to keep the highest modulation possible. So we ignore 10%, but then we know the internal table based on Cable Labs has almost 6 dB of robustness built into the thresholds. So
Right.
we usually say, let's drop our threshold 3 dB to give ourselves more capability to run higher modulation without being premature about going and dropping too quickly.
Mhm.
But and on top of that is, even if you don't drop too quickly and we have another hook, if we get a bunch of uncorrectable FEC, it'll drop anyway.
Okay. So
It's kind of like a catch-all.
I mean, I like this particular example because when we talked last week, not everyone has RxMER per subcarrier capabilities, but they're running OFDM. And one of the things we stressed last week was a lot of times you're if you just look at FBC or you just look at spectrum analysis of your OFDM channel, things may look great. But when you look at the RxMER, things may look really bad, and that explains why your subscribers having
Go back
problems
to
or
your
not able to
diagram.
lock the OFDM channel. This
What was the
example,
level? What was the
what
level there? It was pretty low,
um
right?
so you look at the gray bars, the level of the OFDM channels right around minus 20 dBmV.
Ooh, yeah.
So
So you
I
know what's interesting, and you and I know this. RF levels and RF noise get affected the same through attenuation.
correct.
That's how we keep the same carrier to noise across the spectrum, because as the levels get tilted, the noise also tilts as well. So this is interesting because you're so far into the noise floor of the end device, the modem itself, that the MER is dropping. Like if you normally had tilt going into a house, but the levels were good, your MER wouldn't tilt also. But
Correct.
because you're so low into the noise floor, probably of the modem itself, that lower level and tilt is also equating to lower MER.
Yep. And so I think like using this example, if someone doesn't have our RxMER per subcarrier capabilities, they can at least look at the level and say, hey, if my OFDM channel is at like minus 15 or minus 20, I can probably make the assumption that I'm going to have poor OFDM performance for this subscriber's modem. I have to, just as you're saying, I have to get that OFDM channel out of the noise floor. This goes back to like carrier to noise ratio basics, basic RF 101.
Yeah, yeah. I mean, we'd like to see -5 to +5.
Yeah, I mean, that's the ideal level for all channels that we want in a downstream, -5 to +5. We can go -10 to +10, but you start getting out of that range and,
I mean, the
and bad
original
things,
spec,
bad
yeah,
performance is going to be
yeah,
expected.
yeah. The original 10, 11, 20, 30 spec was -15 to +15, but I'm like, you're just you're playing with fire.
Yes, it's going to get
Yeah.
worse. So, John, that's the last slide I had, and we're just coming up on time here. Anything else you want to cover or mention before we wrap it up for today?
Um, I just saw IBCs going virtual, right? So there's no
Yes, it is.
IBC. Um, we were going to have a Cisco live in February. We just announced that's going to be pushed off and focus more for Vegas, I think in June next year. So we'll see if that still happens.
I think
Cisco,
there'll be a
yeah,
good chance that'll be live by June of next year.
yeah.
We got to get back
And
to
then,
normal.
well, we've been saying that for 2 years, right? What's the next Greek letter we can throw at this next variant? I don't even know what an Omicron looks like.
it's it it's a cron that goes everywhere.
Next one will be the Zeta variant, but then we'll have to move on to something else.
All right. Well, John,
But yeah, it's been good. I mean, everything's been DOCSIS 3.1, more speed. How do I get to 204? Can I really do analog lasers on the upstream with 204? I'm a realist, man. I just don't see it happening. Can I?
204 is going to happen. I mean, I've been talking to more and more operators about 204
Yep.
megahertz in the upstream. I really think we're going to need it.
I think it gives us quite the runway for a while.
Yep.
And because it's there, I can get the modems and stuff to support it now. And we had that talk, right? The 204. So I think it makes a lot of sense, and it gets us to that holy grail of 1 gig upstream.
Yes, 1
We
gig
could get a 1
symmetrical
gig
for
upstream.
everyone.
Yep. I agree.
All right. Well, John, thanks for your time today. Everyone, thanks for tuning in and watching. Please leave us a comment below, and we'll be happy to answer any questions you have. Thanks, everyone. Thanks, John. So long.
All right. Good holidays.